All right. Hi, Professor Lehman. My name is Nathan Reynolds. I am in your ME 304 class on Mondays and Wednesdays, and this is my video tutorial for the problem that you assigned. So this is actually my second time doing the problem just now because the first time I tried recording it, turns out that the software I was using for the free trial only lets you record a video up to 5 minutes long, and I got all the way to the end before I figured that out. So start over, do it again, and here it goes. Hopefully it works. So the strain rosette that we're given is for an AISI 302 stainless steel, and I'm going to just draw it real quickly so I have something up here as a frame of reference. We have our X and Y axis right here. This is Y, this is X, and then the first strain gauge A is on the x-axis, which is very helpful. Then B, down here it's negative 60 degrees. C is down there at negative 120 degrees. So B and C. And from the problem, we see that these are reading. A is 475 times 10 to the negative 6 inch per inch, which is just 475 microinch per inch. B is 200 microinch per inch. And then C is negative 250 microinch per inch. So C is actually going to be in compression, while B and A are in tension. So first we're going to have to find the stresses in the X and Y direction, and then we can use that, and we're going to be able to solve for the stresses in the X and Y direction. All right, strains in X, Y, then the stresses in X and Y, and then the principal stresses. So first, we can see that from the diagram, since A is already in the X direction, sigma X is just going to equal 475 microinch per inch. And then we can use the equations that were given to us in the book and from the lecture that solve for the strains in the gauges B and C using the strains in XY and also gamma XY. So for sigma B, that equals sigma X cosine squared theta B, so the angle between the X axis and the strain gauge in the B direction. That's going to be 60 degrees, but since it's going clockwise, it's actually going to be negative 60 when I plug it in. Then C is 6 degrees from that, so that should be negative 120, but we're not there yet. So 6 degrees, 6 degrees. That's B. And then plus sigma Y, sine squared, sigma B, plus gamma XY, sine theta B, cosine theta B. And then from the diagram again, sigma B equals 200 microinches per inch equals sigma X, which is 475. Cosine squared of theta B will be cosine squared of negative 60 plus sigma Y sine squared negative 60 plus gamma XY sine negative 60, cosine negative 60. We can simplify this down. Where's my calculator? So 475 times cosine of negative 60 squared is 118.75. Subtract that over. So we get 200 minus 118.75. So on the left side, we have 81.25 microinch per inch. And then sine squared, I should remember that from the first time. Sine squared of negative 60 is 0.75 times sigma y. And then sine of negative 60 times cosine of negative 60 equals negative 0.433 gamma xy. This is going to be equation 1. Since we already are given sigma x from the problem, we only really need to get it down to 2 equations and 2 unknowns. So that's why we only have to do simplify the equations for b and c. So this is our first one. Second one is sigma c. Equals sigma x cosine squared theta c plus sigma y sine squared theta c plus gamma xy sine theta c cosine theta c. Plugging in values, we have negative 250 microinches per inch. Sigma x is again 475 microinch per inch. Plus, or times cosine squared negative 120 plus sigma y sine squared negative 120 plus gamma xy sine negative 120 cosine negative 120. Can simplify this down. 475 times cosine squared negative 120 is again 118.75 minus 250, or negative 250 minus 118.75 gives us negative 368.75. So on the left side, negative 368.75 microinch per inch equals sine squared of negative 120. Well, we can see that the sine and cosine values are going to be equal since they're symmetrical across the y-axis. It's just that the cosine value is going to be negative, but the sine values are both going to be negative. But I'm going to plug it in anyways just to be safe. Sine squared of negative 120. Right, just like I thought. Sorry. There we go. 0.75 sigma y. And then plus 0.433 gamma xy. This is equation 2. So now we have 2 equations, 2 unknowns. And to solve this by hand, you could do elimination. You could subtract the problems, cancel out the gamma xy term, solve for sigma y. That will, and then we can in turn solve for sigma y, and then we can in turn solve for gamma xy. But I'm just going to go into my calculator because there is a solve systems equation button. So plugging that in, 2 equations, 2 unknowns, 1.25 equals 0.75 sigma y minus 0.43 gamma xy negative 368.75 equals 0.75 sigma y plus 0.433 gamma xy. So that's going to come out to us having there we go. Sigma y equals negative 191 micro inches per inch, and then gamma xy is going to equal negative 519 microradians. All right, now that we have that, and we were already given our sigma x, we can now solve for the stresses in the x and y direction and tau xy. And then we can use that to do our Moore circle. But the equation for sigma x is the modulus of elasticity. That is really annoying. It's never great. Modulus of elasticity. There we go. 1 minus Poisson's ratio squared over sigma y plus Poisson's ratio sigma x. So for Poisson's ratio, it's going to be the negative lateral stress over the negative lateral strain over the positive horizontal strain. Yeah. And it's going to be, which is the same as, at least for this problem, negative sigma y over sigma x, which is 191 over 475, same units, so the units cancel out. And that equals 0.402. So that's our Poisson's ratio. Modulus of elasticity, look it up in the textbook for A1S1302 steel. I looked it up earlier, and it came out to be 28,000 KSI. All right. So now we'll just plug in our values. 28,000 KSI over 1 minus. I don't know if you can hear that, but my roommates are playing Xbox. I'm sorry. Squared. Sigma y, 475 microinches per inch. Or no, sorry, that's wrong. My textbook, my notes or something. Sorry, 1 second. Yeah. So sigma x is not actually, or I've been saying sigma this whole time. This is sigma. This is epsilon. I'm so tired. Sorry. Yeah, I have been saying it wrong this whole time. So epsilon y, or sigma x, equals modulus elasticity over 1 minus Poisson's ratio minus epsilon x plus Poisson's ratio times epsilon y. All right, that should be better. So epsilon y equals negative 191, or epsilon x equals 475 microinch per inch. Times Poisson's ratio, 0.402, times epsilon y, which is negative 191 microinch per inch. Put in my calculator. 28,000 divided by 1 minus 0.402 squared times 475 plus 0.402 times negative 191. Except since 475 is in microinches per inch, I'm actually multiplying it by 10 to the negative 6, and 191 times 10 to the negative 6. So sigma x, sigma x. I don't know why I'm getting my Greek letters mixed up right now. It's just been a very long day. Sigma x equals 13.3. It's KSI. And then for sigma y, the equation is modulus of elasticity over 1 minus Poisson's times epsilon y plus Poisson's times epsilon x. Plugging in for this one, modulus of elasticity is 28,000 KSI over 1 minus Poisson's 0.402 squared times epsilon y, which is negative 191 microinch per inch plus 0.402 times 475 microinches per inch. All right, so solving that, 28,000 over 1 minus 0.402 squared times negative 191, 10 to the negative 6 plus 0.402 times 475, 10 to the negative 6. That gives us, for sigma y, negative 0.00167 KSI. Then tau xy is equal to the modulus of rigidity times gamma xy. Modulus of rigidity, from the textbook, again, I looked it up earlier. 10,800 KSI times negative 519 microradians. And don't forget to multiply that by 10 to the negative 6. So tau xy equals negative 5.61 KSI. So we have our sigma x, y, or sigma x, sigma y, and tau xy. Now we can use this to draw our Mohr circle and find our principal stresses and maximum shear stress. So I'm going to move the canvas down again. Yeah, okay. So all right. So this is our tau axis, this is our sigma axis. We're going to start with sigma y when you're doing the Mohr circle. But since our tau xy was negative, we're going to start going down to negative 5.61 KSI. This one's positive 5.61 KSI. Starting with sigma y, which came out to be 0.00, negative 0.00167. That's going to put us like right here. And then for sigma x, which was 13.3, yep, up to 5.61, should put us right there. Connecting these, this should be our sigma average, or just the distance, or equidistant between them, the midpoint, which we can find by adding negative 0.00167 and 13.3. And dividing it by 2. So sigma average equals 6.65 KSI. So now that we have found the center of our Mohr circle, we can just go ahead and draw the circle. Hopefully like somewhat neatly. It's really hard to do on a virtual pen pad, but all right, close enough. So there's that. Now we can solve for the radius using the Pythagorean theorem. It's just going to be your sigma average and your tau xy. So radius equals 6.65 squared plus 5.61 squared square root so the radius is 8.7. Principal stresses are going to be in this part of the circle, so sigma average plus the radius, so sigma 1 equals 6.65 plus 8.7. Sigma 2 equals 6.65 minus 8.7. And our tau max, which would be straight up right here, that's just going to be equal to our radius, which is 8.7. Tau max is in radians. Sigma 1 is equal to 15.35 KSI. And 6.65 minus 8.7 equals negative 2.05 KSI. And that should be our final answer. The principal stresses are 15.35 KSI, negative 2.05 KSI, and then tau max 8.7. All right, that should wrap it up. Hopefully this one actually uploads. Thank you for listening, and I will see you on Monday.